Hello and welcome to TidyX episode 183. TidyX's screencast where we go through and explain how our code works. My name's Ellis Hughes.
And my name's Patrick Ward. Thanks for checking in with us at TidyX, episode 183. And we are going to move into talking about the purrr package, which is a
Yes.
super helpful package for making your life a lot easier when you need to do a whole bunch of repeated tasks that you might otherwise maybe do in a for loop, or maybe
A
very
lot.
unconventionally might do with copy and paste, and repeat like that. But if you're working with loops and lists, and you're doing so in tidyverse, purrr is a part of the tidyverse suite of packages, and it's super helpful to do that. So this week we're going to kind of tease an example that you might use purrr for, which is which is building within group models. In this case, we're going to use regression. You could use any model you want, though. It doesn't really matter here. The whole point is that we're going to build models, predictive models within groups. So let's say we had groups that we wanted to build stratified models against. And instead of doing the old copy and paste or for loop, we're going to show you how to do that in purrr. And then over the subsequent weeks, we're going to unpack that a little bit. As always, be sure to like and subscribe on the YouTube channel, and drop your questions, comments down below if you want to see more of this kind of stuff.
Yep, exactly. So to get started here, we're going to load the library tidyverse. That's going to have the purrr package included when it gets attached, as well as all our other data manipulation type tools. The broom package is going to be what we're going to use to clean up the model afterwards to show all the coefficients and all the various results of the model. And then the data set we're going to be using today is the Palmer Penguins data set. So we're gonna load Palmer Penguins. After we do that, we're going to do a few plots today too. So we're going to set the theme to be the light theme on ggplot because we think that looks nice. To load the data from the Palmer Penguins library, we go data penguins, and that just attaches it to our namespace here. You can now see it in our environment here as a promise. You don't have to assign it to D because penguins does now exist, but this was just so we don't overwrite penguins. So we're going to assign that to D, and we can do a head on D, and we can see that the Palmer Penguins data set is relatively simple. It's about penguins on the Palmer Islands, and there's 3 different species that they've got here. And on top of the different species, there are a number of penguins. They have information about like what island are they on, bill length, bill. Okay, we're just gonna do
Build depth, build length, flipper.
island,
There
depth,
it is.
length, flipper, body mass, sex, year. So a whole bunch of metadata about these penguins, or I guess not metadata, but just data.
Mhm.
So how are we going to go about what are we curious about here, Patrick? What are we
So
trying
we're
to
going to
calculate?
build, yeah, we're just going to build a simple model of bill length. And for the purposes of this, of course, we could build this model and make species an actual coefficient in the model. But in this case, we're just going to build the model and we're going to stratify it on species, which means each species is going
Okay.
to get, each of the 3 species is going to get their own linear model. And that linear model is going to be the flipper, or the bill length, which is going to be estimated from the flipper length, the body mass, and the sex of the penguin.
I mean, if you wanted to do this manually, you do it like this, where it'd be like filter species
Yeah,
equals
a deli or something.
deli. Right. But that, if then you then copy and paste it for, the next one and the next one, obviously not very good.
No, yeah.
So how can we do this? And then what if we update the data set too and we get a new species that's
Mhm.
included? Um,
Yeah.
there's a lot of different ways where this programmatically approaching this, so it solves it for this problem and then potentially future situations that we might be in, is always a good way to start thinking about how you're writing your code.
Yeah. So one way we can do this is we can take our data set and first just use the split function on species. So what this is going to do is it's going to create, in this case, 3 separate lists, one for each of the species, the Gen2, the chinstrap, and the deli. And then once they're in these lists, we're going to use map to say, hey, map, over each of these lists, build that linear model that Ellis wrote up at the top. And so we just do that with map function. We give it the tilde because then we're going to pass a function after the tilde. And the data is .x, which is saying each of the data frames within each of those lists. Ooh, there we go.
There we go.
And then the final step is, now that we have all of the, this is our typical linear model just written as a list. We could, of course, stop there and call each of these if we wanted to, in list with a list call. But maybe we want to fix this up and make it look nice. So one of the ways we can do that is use map DFR, which is going to obviously underscore turn it into a data frame. And in order to do that, we need to organize those coefficients in a way that a data frame can accept them. And so the tidy function from the broom package gives us an opportunity to do that. We've talked about the broom package before, but it's a nice way to take these linear models, or take really any type of models, and get the information you need into a nice and clean data frame. And so what mapDFR is going to do is it's going to say, take that tidy function, go into each list, grab the information we need, organize it as a data frame, and then stack them all together. And so we're also going to add then a column that's called species, which is going to be the ID of each of these linear models. So if we run that, not delete it, we get a nice data frame. We could see species. It's repeated 4 times to give us 1 row per model coefficient. So the intercept, the flipper length, the body mass, and the sex of the penguin. And then we have all of the information that's contained within that linear model call. So the beta coefficient, its a respective standard error, the test statistic, and then the p-value of that coefficient. And so now that we have that all organized, we can do things like maybe plot it in a nice way. So we're just going to remove the intercept term, and we're going to keep the other estimates. We're going to plot them as geome points. We're going to fill them by species color. We're going to add 2 times the standard error. So we'll add the 95% confidence interval around each of the beta coefficients. And then we're going to do a facet wrap, and we're going to put those into a facet for each of the terms. And we'll set scale to free because we didn't standardize these variables first. They're going to be on different scales, so it'll be hard to see the standard errors on some of them. And so now we have our nice coefficients, and we can start to make some inference about the different relationships that these variables have to bill length.
Yep.
With respect to species. Yeah.
Exactly. So you can see here, like the Gen 2 body mass is has for every 0.001 increase. Wait, am I interpreting that right? Then it's a 1 step increase in the
for every 1 step increase in what is that body mass, there is a 0.001 increase in bill length.
Yep.
We can see like some pretty considerable overlap, maybe, but like by sex, we can see that there are some differences. For when it's a male and it's a chin strap, there seems to be a larger increase in bill length compared to maybe the Gen 2. And same thing with flipper length. It looks like the Gen 2, for every 1 unit increase in flipper length, there seems to be a larger unit increase in bill length for the Gen 2 penguin.
All right.
But why stop there? What if we wanted to make predictions with this model and see how well those predictions do?
Yeah, let's do that. So what we're going to do is we're going to take the penguins data set, and we're going to use the function drop NA. So that'll remove any of the rows that have NA values. And the reason we're doing that is because we can't predict from an NA. So we need to remove that. And then again, we're going to group by species and nest it. So nesting it is going to take all the data, take the data set and put it in for each species and put it into its own tibble. So let's take a look at what's happening here. So see, we have got species Adelie, Gen 2, and Chinstrap, and then their respective tibbles, right? We're then going to apply the same sort of structure here. We're going to take the penguin's nest. We're going to use the mutate function. And this time, rather than doing that split that we did earlier, we're now within that mutate going to say, hey, map across the data column, and again, fit that same model that we just had talked about. And then we're going to assign that to fit. So we're going to create basically a list column in this data set that is called, the title is called fit, and that's going to store the model for Adeli, Gen 2, and Chinstrap.
So can
Then,
we pause right there for a second?
yes,
So can we just explain why in this map we had to write a custom function versus before where we just dropped the tilde in front of the lm?
the reason you had to write this function is because you're using df here, because you're trying to apply this to every single entry here, as
Yep.
opposed to how we had it before, where it was just mapping across everything.
Mhm.
Though there's a variety of different ways you can write this though. So there's no like whatever works for your brain is the right way to write it, like
Yeah, this
functionally.
is how I wrote it, but I mean, I'm sure there's a different way or
You could
yeah.
probably do something like
Yeah, maybe
that.
that would work.
This should work.
Yeah, and you don't need the tildes.
Yeah.
Is that gonna work?
Yeah, so you can write it like this. So the .x moniker is if you write this anonymous function for map, .x is that first entry here.
Yeah, the first entry there.
So we can do that, and then we can do map on fit predictions to get the predictions for every single then data point as well. So we can do that. Now we've got our penguins prod, and so now we've got a tibble that's got the species, the data set, the linear model, and then the predictions on bill length for every single penguin. And so now we can call unnest on the pred, and we can then now get every single row for the Adeli. Okay, they predicted for the first penguin 39.6, then 37.7, 37.4, blah, 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 all the way down. And so this is like we basically re-blew out um, the tibble again. And so then we can, what are we doing here? We're going to tidy the fit models just like we did earlier. And this looks, it just kind of keeps on getting bigger. So again, we've got the Adeli, the intercept, Adeli, flipper length, Adeli, body mass, Adeli, sex, and again, the various estimates, standard errors, statistic, and p-value as
Mhm.
well, going out that way. So it's another way that you can kind of look at this. I might do more of a and then select at this point because it's not helping me data fit, just dropping some of these because it's
Yeah.
just getting a little wide. So like I'd probably do it like that.
This is really one of the values of, tidyverse is the ability to have a tibble that stores lots of various information in list columns, which
Yes.
you can then unnest when you need them, or keep them in folded lists when you don't need them. And you can have a lot of information staying with you and carrying on through your code.
Yep. So then for the last trick that we're going to show you, what we're going to do is we're going to take those predicted values and we're going to then compare them against the actual values, and then we're going to color them by the species. So you can compare like the model, how is a particular model under predicting or over predicting generally for each species. So maybe one's harder to fit than the other. So we're going to take penguins pred, we're going to unnest data and select species and bill length. So this is getting the original data set, the original values for bill length. Now, if we wanted to get the predicted ones, again, we're going to take the penguins pred, we're going to unnest the pred results, ungroup those, and select out pred. So this is making the assumption, and then we're going to c-bind it together, which is vertically, it's column bind, c-bind. So we're going to add it on to it. And so when we do that, we end up with a data set that looks like this, where we have the original bill length and then the predicted bill length. And you can already see they're like not too terribly far off. We then throw it into a ggplot. Our x-axis is our model predictions. Our y-axis are the true values. We're going to color it by species. We're going to say, hey, actually make it all points of size 4. And then let's add a slope line where it's an intercept of 0, slope of 1. So we're just assuming like this would be perfect prediction between the two. We're going to set that color to be black, the size of that line to 1.2, and we're going to make it dash. So it's a little bit lighter visually on there. And once we do that, you can kind of see that there is obviously a big difference in the Adelie versus the chin strap in Gen 2 in terms of overall bill length. But then you can kind of see it clusters a little bit
Yeah.
between these two predictions, and then these are a little bit scattered. But it doesn't look like any one model necessarily under or over fits consistently. Like it's all kind of scattered around the 45 line. I mean, there's this one chin strap here where apparently it predicted way below, but that could have been like an outlier too for the model, and it just can't deal with that. Or we need to make a better model or more information. I don't know. There's a whole bunch of different ways you could look at that. Or maybe linear
Mhm.
model is not the best way to model this. There's a lot of different things, but yeah, so that's how you can use purrr to create by group models, and then how you can take that and continue to build off of that and add more information or add more predictive values out of it, and then ways that you can actually look at the results. Patrick, do you have anything else you want to say about it?
No, this is purrr is a pretty powerful package. There's lots that you can do from both the data cleaning, data engineering, feature engineering side, as well as the model fitting side, which is sort of like tidy models tried to take that and wrap it all together with a bow. But you could, of course, do these things yourself and not rely on tidy models. Maybe do them yourself in terms of trying to get your own head around what's going on. So we'll, in the subsequent weeks, we'll go through more of the purrr package and talk about more ideas and ways to use this for things like data engineering and feature engineering and model fitting.
Yeah, and leave a comment down below ways that you'd like to see us using purrr to solve problems. So with that, I guess we're going to call episode 183 of TidyX. Thank you all so much for joining us. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
And my name's Patrick Ward. You can find me on X at OSPPatrick at tidy_explained is where the screencast lives on X. Of course, easiest way to hit us up, YouTube channel, questions, comments down below, get your questions answered on the air. And as always, if you enjoy the work that we're doing and you'd like to support the show, we do have a Patreon page and we're super appreciative of anything that you'd like to give.
Thank you all so much, and keep on exploring your world.